Thanks for listening, space fans. This is the 20th episode of Are We There Yet? So I just wanted to thank you for listening to all these great conversations about space exploration. Now, we can keep the conversations going strong by having you make a financial contribution to WMFE. That's the station where we produce this podcast. You can do that by visiting wmfe.org/support. And don't forget to rate us and give us a review on iTunes if you like the show. That's how more people find out about it. So thanks. Now, let's talk space. From the studios at WMFE in Orlando, Florida, this is the Space Exploration Podcast that asks the question, are we there yet? Hi, I'm Brendan Byrne. We talk a lot about the hardware that's going to get us to Mars, but the most important thing about human spaceflight is, well, humans. There's a lot of research going into the impact space travel has on the body. Just think back to Scott Kelly's year in space. But we're going to have to jump over quite a bit of physiological hurdles when traveling to deep space. There's the issue of living in reduced gravity, dealing with radiation, nutrient deficiencies, all sorts of challenges. And there's also the immune system. Now, my next guest found something rather interesting about astronauts. When they came back from space after spending multiple months, they were getting sick. And not like a cold or anything, but viruses that should have been kept in check by what they call Tcells. Dr. Krishna Kamanduri is a researcher at the Sylvester Comprehensive Cancer Center at the University of Miami, and he's looking into what causes the flare-ups of dormant viruses in astronauts. Krishna, thanks for speaking with me.
Thank you.
So let's first start with these Tcells. First of all, what are they, and how does the body make them?
So T cells are the primary cells in our bloodstream that protect us from many different types of infections, especially infections like that are caused by viruses and fungal organisms that live in the environment. So when we get influenza or when we get the common cold, the immune cells that are most important in clearing those infections that are, of course, very common and can be, in some cases, mild infections, in some cases, life-threatening infections, are T cells. And to put it in another way, HIV disease, which is a disease that, of course, we've all learned a lot about over the last few decades, HIV disease is a disease that leads to the destruction of just one type of T cell. So that's an illustration of how important T cells are to our immune system and how the loss of even one of the subsets of T cells can actually cause very serious consequences for human health. So T cells are actually produced in an organ called the thymus. And believe it or not, when I went to medical school a little over 20 years ago, it was felt that the thymus was actually not an organ whose function persisted into adulthood. So we knew that the thymus produced T cells. And in fact, T cells are called T cells because they're what we call thymus-derived T cells, or that is produced in the thymus. The thymus is an organ that sits basically above the heart in the chest, and it then produces T cells that have a very broad, what we call repertoire, or ability to recognize a very broad range of different antigens or targets, which are present on the surface or parts of various organisms. So a very broad repertoire or diversity of T cells allows us to basically encounter viruses or other pathogens that we may see decades after producing the T cell that will eventually expand and help to control that infection. So that's basically what we chose to study in the context of our work, is how the thymus produces T cells in healthy individuals, and how under certain states in either healthy individuals exposed to stress or patients who have various diseases, the function of the thymus changes and how that can affect the immune system.
So let's talk about the study that you were a co-researcher on here, because you looked at a very interesting set of subjects. Go ahead and tell me a little bit about that.
So we had been interested in studying, again, the role of the T cells in typically in patients with diseases like HIV disease or patients with cancer. And we wanted to know how the function of the thymus might actually be important in rebuilding the immune system or helping to preserve the function of the immune system. But we were, when the work began, actually, I was at the University of Texas MD Anderson Cancer Center, which is in Houston, Texas. And of course, we all know that Houston is close to Johnson Space Center. And we actually had a collaborator who at that time approached our laboratory and approached me because of my prior expertise in understanding how to assess T-cell responses to individual viruses. Because he actually told me that he had some interesting data that individuals who had flown on the shuttle or individuals who had flown on the International Space Station appeared to have evidence of reactivation of viral infections that we typically didn't see in healthy individuals. And so he actually relied on me to help to develop or improve assays that were already set up in the laboratory to assess human T-cell responses to individual viruses. And at that time, we had started this work on looking at the function of the thymus or how the thymus actually produces T-cells. And we suggested to this collaborator, Ray Stowe, who again was at Johnson Space Center, and his collaborators, that perhaps in studies going forward that we could actually assess and measure thymic function, that is the function of the thymus to produce new T-cells, to complement the work that they were already doing to look at the various numbers of white blood cell and T-cell subsets, as well as the function of T-cells. So we thought it would be fun. Obviously, we were excited, as many researchers are, about the importance of the space program. But we also thought it would teach us about a different group of subjects that we wouldn't normally study, that is healthy individuals that are exposed to stress, in this case, in the context of an interesting occupation.
What were some of those viruses that were coming back?
So the viruses that Ray and his colleagues, Dwayne Pearson and Satish Mehta and others, Clarence Sams, had shown were reactivated were two viruses that are of a class of viruses called herpes viruses. And these are viruses that individuals may be familiar with. One of them more commonly than the other one, and that the first one is Epstein-Barr virus. Epstein-Barr virus is actually the virus that causes infectious mononucleosis, which some individuals will know as the kissing disease. It's a disease that is often acquired in adolescence, and it can be associated with fevers and sometimes sore throats and sometimes fatigue during the primary course of infection. The second virus is a virus called cytomegalovirus, or CMV, and CMV is typically acquired very early in youth. In the world, about 70 to 80% of people acquire CMV infection at some point. In developed countries, it's a little bit less, and in parts of the developing world, nearly everybody acquires CMV in childhood. Epstein-Barr virus, like CMV, is acquired by more than 95% of the world's population. And the interesting thing about both of these viruses, CMV and Epstein-Barr virus, is that typically when we get infected, again, usually again in childhood or adolescence, we don't clear those viruses. Those viruses stay persistent in our bodies for the rest of our lives. And indeed, what keeps the viruses from actually causing serious infection are our T cells. So our T cells basically keep the viruses in check. Now, in HIV disease and after bone marrow transplants, and I'm a stem cell transplant and bone marrow transplant physician at the Sylvester Comprehensive Cancer Center, patients who have weakened immune systems following chemotherapy can actually develop severe and even life-threatening infections due to cytomegalovirus and occasionally due to Epstein-Barr virus. And the same is true in HIV infection. HIV infection can lead to blindness due to CMV, lung disease due to CMV, and also some lymphomas, a type of cancer associated with Epstein-Barr virus. But what our colleague Ray Stowe showed previously was that healthy astronauts had a high degree of very short-term reactivation of Epstein-Barr virus, which he either measured by an assay in the blood or for cytomegalovirus, shedding of virus in the urine, which is not typical in healthy individuals. And that suggested to him that in some way during short-term spaceflight that the immune system wasn't doing what it should do, and that either the cells that control CMV and EBV, the T cells, were either decreased in number transiently, which he actually found not to be true, or that they effectively became non-functional, which he showed in other assays was the case, that that these cells weren't functioning. So we already knew on the basis of this work that had been done at JSC that T cells could effectively become non-functional, leading to short-term reactivation. We don't know that that caused any serious disease in those patients. But we had shown in my laboratory that stem cell transplant recipients also, sometimes especially when they were given steroids for the treatment of diseases that can happen after transplant, that their T cells effectively became non-functional. And that, in the case of stem cell transplant patients, actually led to infection and also disease that could be life-threatening or even fatal. So we had some complementary data, albeit in very different patient populations. And we thought it would be interesting to then also study whether T cell production was affected through spaceflight.
I don't want to jump to any generalizations here, but from what you're saying, spaceflight is almost as harsh on the immune system as something like chemotherapy and a bone marrow transplant.
Well, I would say it's not. I wouldn't go that far because we don't have any evidence that the stress of spaceflight leads to actual infection that leads to hospitalization or it becomes life-threatening. Where in the setting of diseases like HIV disease and after stem cell transplants, we know that those things can happen. So, but what I would say is that it appears that there is a transient state that astronauts are exposed to that in some ways, perhaps in a more minor way, mimics what's happening in these more severe disease states like HIV infection and cancer after chemotherapy.
So, Krishna, tell me about the astronauts you looked at. How many of them were there? How old were they? And how long had they been in space?
So there were 16 astronauts that we studied, and their ages were, again, typical for ISS astronauts, that is, usually in their 30s and 40s. And they spent a mean number, there's an average number of around, again, the time that they spent in space was between typically 2 and 6 months. So there were obviously variable because space flights were shorter in some individuals and longer in others.
Now, is there any? Do you have a hypothesis as to what is causing this drop in T cells after being exposed to space travel?
Sure. Well, so what we actually found was actually that the T cell numbers before and after spaceflight were not grossly changed. There are other changes in total white blood cell counts, but what we actually found was that newly produced T cells, and we call these recent thymic emigrants because they have come out of the thymus, which is the organ that produces those T cells. So what we did in this study is we actually had developed a novel assay. We and others had developed assays to basically measure the very small fraction of T cells in the peripheral blood that had been recently produced in the thymus. So just to put it in perspective, when we looked at 1 million cells that we call peripheral blood mononuclear cells, or cells that, again, are the cells that include T cells, roughly healthy individuals beforehand had on the order of thousands per million peripheral blood mononuclear cell of cells that were recent thymic emigrants. So somewhere between 1 in 100 and 1 in 1,000 T cells were recently produced by the thymus. So this was basically by this assay, again, measuring DNA of T cells in the peripheral blood, what we call PCR, we were able to assess the number of recent thymic emigrants. And what we found was that in these 16 astronauts, we measured them an average of 3 times before spaceflight, and on average they had around 3,500 cells that were recent thymic emigrants for every 1 million cells in the circulation. When we looked at them on the day that they returned from space, that number dropped to between 1,700 and 1,800 on average, which is about 45% on average. Interestingly, when we looked at them in the weeks following spaceflight, the numbers of recent thymic emigrants came back up again. So that told us that there was both a decrease in the number of T cells being produced, but that the number rebounded once they returned to Earth and recovered from spaceflight. Now, unfortunately, in this study, we did not have samples that were drawn during spaceflight. So what we can't really say is this a consequence of orbiting the Earth and microgravity, or is this a consequence of the enormous stresses that astronauts, of course, experience on reentry? But what we can say is that clearly, statistically, when individuals returned from space and were drawn on the day of return from space, that they were producing about half as many T cells as they were on average in the 3 times that we assessed them prior to space travel. Now, what we think that was responsible for this is actually the production of what we call stress steroids. So many individuals may know that we use a class of medications called steroids to treat inflammation. So Cordaid, for example, is a topical cream that we might put on a rash. And some individuals may have been given prednisone for an asthma attack or for poison oak or for example, for other autoimmune diseases. And these class of medications called corticosteroids are basically similar to what our own body produces in a stress response. So it's been termed the fight or flight response. We actually produce these steroids in our own body, probably to help our own body deal with stress and inflammation. And it turns out that when we measured both urine and blood steroid amounts, that the amount of steroid in 15 of the 16 astronauts basically doubled at the time that they returned from spaceflight. So what we saw was that steroid amounts, these endogenously produced, so that is produced within our body, steroid amounts, basically increased from before spaceflight to return to after spaceflight. And in parallel, the thymic production, that is the production of T cells, was higher beforehand, dropped at return, and returned to normal afterward. So while we can't precisely connect the dots, that is proving that the increase in steroids was associated with the suppression of T cells, we know that if we take animals, for example, a very outstanding T cell biologist who studied chickens actually early on gave steroids to chickens, and he showed that the chickens' production of T cell dropped again whenever they were administered oral steroids, or I should say intravenous steroids, just like when a healthy individual takes oral steroids. When they stopped the steroid administration to the chickens, the T cell production went back up. So what we saw in humans is certainly very similar to what has recently and previously been shown in animal models. So we presume, though we don't have direct evidence linking those two, that's the case, that our body is basically reacting to stress, producing steroids, that basically suppress the production of the T cells. Now, what's interesting is that our work in the context of patients after stem cell transplants who have been given steroids because they needed steroids to treat inflammatory conditions, that those T cells also basically stun the function, that the steroids stun the function of T cells and allow them then to be non-functional and leading to the reactivation of those viruses that I talked about beforehand. So what this suggests is that stress can really affect our immune system in 2 ways. One that was known, that is that the T cells that are really critical for the control of these viruses can be inactivated, but also that the production of T cells can be suppressed, and that was something that we haven't shown in healthy individuals, who experience a stress state.
Krishna, you mentioned that the astronauts in your study spent between 2 and 6 months on station, which is pretty average mission duration for them. But when organizations look towards long-term space flight, looking at years and many months after that in space, is there a desire to get to the bottom of this and make sure that they're staying healthy, specifically this T cell drop?
Yeah, that's a great question, and certainly one that was raised by our studies, and indeed, again, our collaborators who are primary NASA and space immune function researchers were very interested in. Clearly, what I'm telling you is at least we don't know that short-term space flight causes profound changes in the immune system that lead to disease, at least as far as we know. But it's possible that in long-term space flight, again, if you travel to Mars and back, where again the amount of time spent in transit would be years, that immune function could actually decline if these were persistent and progressive effects that actually lead then to significant changes in immune function, in which case then we would need to really find ways to counteract that, I think, through novel strategies. We don't know the answer to that, and I think one of the things that this suggests is that further studies are really needed. We are hoping that additional studies that have, again, by our collaborators that have already been proposed, will allow more frequent sampling, including sampling while patients are actually orbiting in the International Space Station, to help us to understand whether this is really a reentry related stress event or whether again, it's something that happens in microgravity or happens while orbiting. And also, I think critically, is duration of travel associated with the degree of the magnitude of the effect that we're seeing, because I think that those are things that could definitely affect immune function over time, and what we would not want are serious health consequences. Because one thing we can do is we can prevent astronauts from exposure to cold or flu viruses or other viruses that are transient. But again, since most of these viruses, in fact, the vast majority of the world's population has both of these viruses and other viruses, the virus that causes chickenpox, the virus that causes cold sores. These are viruses that are, again, acquired early in life and are kept in check by our T cells. So you could imagine that if there were global effects on both T cell function and the production of T cells, and they were progressive over time, that would certainly be potentially cause for concern. And I think it tells us that we really need more study in astronauts. And from my perspective, as somebody who obviously doesn't typically take care of astronauts, but typically takes care of cancer patients, we can imagine that similar stress events can cause problems in healthy individuals who undergo chemotherapy, for example, both because of the emotional stresses and physical stresses. I think we all know can relate to individual events where you're studying for a test or you're working very hard on a work deadline, and you get cold sores or you feel unwell. And we think that we always talk about connections between stress and the immune system, but I think we now have at least a hard link, at least in an unusual situation.
I've been speaking with Dr. Krishna Kamanduri. He's a researcher at the Sylvester Comprehensive Cancer Center at the University of Miami. Krishna, thank you very much for speaking with me.
It was really my pleasure. Thank you so much for inviting me.
Well, that's it for this episode. Support for Are We There Yet comes from the listeners of WMFE. You can follow the show online. We're at AWTY Mars. Are We There Yet Mars? Get it? Or reach out to me in the Twitterverse. I'm at Space Brendan. Let's have a conversation. Are We There Yet is a production of WMFE. Our theme music was composed by Kevin McLeod. For more space news, visit us online at wmfe.org/space. And until next time, I'm Brendan Byrne. Thanks for listening.